Section. Introduction. We're going to delve into the fascinating world of creativity, a trait often considered uniquely human, but one that's also a powerful force driving societal transformation and progress in fields like science, technology, and the arts. Creativity is the engine of innovation, sparking economic growth and social change. In our digital age, artificial intelligence, AI, has opened up new possibilities for creative pursuits. Advanced AI models, powered by deep learning, have shown impressive abilities in solving complex problems, such as creating new drugs and proteins. They've also demonstrated artistic flair, composing poetry and crafting stories. These AI models have even shown a knack for generating fresh ideas, outperforming MBA students in the quality and uniqueness of their innovative product and service concepts. As AI's creative abilities continue to evolve, it's becoming harder to distinguish between human and machine-generated work. This raises important questions about the nature of creativity, especially when it comes to AI. While human creativity has been extensively studied in fields like psychology, philosophy, and cognitive science, there's still no agreement on what exactly creativity means. This is largely due to the subjective nature of the term. Even if we accept the common definition of creativity as a combination of novelty and quality, these criteria are inherently subjective. What's considered new and high quality can vary greatly across different cultures, disciplines, and time periods. This lack of consensus on what constitutes human creativity makes it even more challenging to understand and develop creativity in AI. In the realm of AI creativity, AI models are designed to generate outputs that mirror their training data. This raises important questions about the originality of their creations. Are they truly unique, or just rehashed elements? This complexity adds another layer of difficulty to defining and analyzing creativity in AI. Given these challenges, it's crucial to establish an objective framework for evaluating AI's creativity. This is a key step towards responsibly developing and further assessing AI systems. In our work, we aim to create a solid framework for exploring creativity in AI. Instead of trying to answer the question, can AI be creative? A question that's fraught with the difficulties of defining creativity. We focus on a more concrete question. Can AI be as creative as humans? To structure this question, we introduce the concept of relative creativity. In this context, an AI model is considered as creative as a hypothetical human creator if it can produce works that are indistinguishable from that creator's, as judged by an evaluator. We propose a method to assess whether and to what extent a model achieves relative creativity through statistical creativity. This method involves comparing AI outputs with those of actual human creators, along with a theoretical guarantee that statistical creativity is a practical and valid measure of creativity. In line with recent advancements in large language models, LLMs, such as GPT-4 and Llama, our research explores statistical creativity in autoregressive models that excel in predicting and generating the next token within a prompting paradigm. To link the theoretical quantification of creativity with practical methods for achieving creativity in model training, we introduce the statistical creative loss. This loss function provides a viable strategy for fostering statistical creativity during training. The corresponding analysis also clarifies the relationship between the log likelihood of next token prediction and the necessary volume of training samples required for developing models capable of exhibiting statistical creativity. In summary, our framework offers a comprehensive, evolving methodology for evaluating and enhancing statistical creativity in AI, effectively bridging theoretical concepts with practical application. In our effort to create a solid framework for exploring creativity in AI, we introduce the concept of relative creativity. This concept suggests that an AI model can be considered as creative as a hypothetical human creator if its outputs are indistinguishable from those of the creator, as judged by an evaluator. However, applying this concept directly to AI model evaluation encounters practical challenges, mainly due to the hypothetical nature of the creator, which hinders empirical validation. To overcome this, we present statistical creativity, a methodology that makes assessing relative creativity both feasible and realistic, anchoring it in the context of existing individuals' creative outputs. We delve into autoregressive models, a common technique in generative models, introducing autoregressive statistical creativity. We also apply this framework to cutting-edge model paradigms, like prompt-conditioned large language models, LLMs. This section unveils prompt-contextualized autoregressive statistical creativity. We introduce the statistical creative loss, bridging the theoretical-practical gap and providing actionable guidelines for training creative AI models. The analysis here clarifies the relationship between the upper bound of next token prediction log likelihood and the required volume of training samples for achieving statistical creativity. Our findings highlight that the quantity of creator-creation pairs are crucial, rather than merely having a large volume of creation data. This insight makes the concept of statistical creativity particularly applicable in current AI frameworks based on next token prediction. We hope this paper not only offers theoretical perspectives but also guides the discourse on AI creativity, advocating for relative evaluations to spur empirical research and establish a framework for assessing and augmenting the creative capabilities of AI models. Section Summary. In this section, the authors discuss the importance of creativity in both humans and artificial intelligence, AI. They highlight the challenges in defining and evaluating creativity, especially in AI, and propose a framework called relative creativity, which compares AI outputs to those of human creators. They introduce the concept of statistical creativity, which allows for empirical validation of relative creativity by comparing AI outputs to existing human creative outputs. The authors also explore autoregressive models and prompt-conditioned large language models, LLMs, within this framework and introduce the statistical creative loss as a method for training creative AI models. Overall, their framework aims to provide a comprehensive methodology for evaluating and enhancing statistical creativity in AI. Section. Relative creativity. Let's talk about a new concept we're introducing called relative creativity. Instead of trying to define creativity in absolute terms, which can be quite challenging, we're proposing a different approach. This approach is similar to the Turing test's method of evaluating intelligence. In the Turing test, a machine is considered intelligent if it can respond to questions in a way that is indistinguishable from a human. Similarly, we're suggesting that an AI model can be considered relatively creative if it can produce work that is indistinguishable from that of a hypothetical human creator. This concept of relative creativity is dependent on the individual to whom the AI is being compared. For example, an AI might seem very creative when compared to a non-expert human, but less so when compared to an expert artist or designer. This approach acknowledges the subjective aspects of creativity, such as originality and problem-solving skills, and incorporates them into the evaluation process. Now, let's get into the technical details. Imagine we're trying to get an AI to write poems. We have a set of poems, and a generative model that takes in certain information about poets, such as their background and education. The model then produces a poem based on this information. We also have a set of complete information about poets, but we only give the model a subset of this information to prevent it from simply copying existing poems. We define a probability distribution over the set of all possible creators, which includes poets from the past, present, and future. We also have an evaluation function that determines whether the AI model is able to mimic a particular human creator. We define AI creativity as the ability of the AI model to mimic a hypothetical human creator, based on the information given about this creator. This concept is formalized in our definition of relative creativity. However, measuring this in practice can be difficult, as the hypothetical human creator doesn't actually exist. To overcome this, we need a theoretical framework that can link our definition of relative creativity with real-world data. To measure relative creativity, we propose a method that evaluates the creative potential of an AI model based on the observable outputs of existing human creators. We introduce a metric called statistical creativity, which estimates how similar the creative abilities of an AI model are to those of human creators. A low value for this metric indicates that the AI model's outputs are very similar to those of human creators, making it difficult to distinguish between the two. We also present a theorem that outlines the conditions under which an AI model can be considered to exhibit statistical creativity. Specifically, if certain conditions are met and we have a large enough sample set for evaluation, then the AI can be considered as statistically creative as the humans in the sample set. The proof for this theorem is provided in the appendix. Section Summary. Relative creativity is a concept proposed to evaluate the creativity of AI models without relying on absolute definitions or checklists. It suggests that an AI model is considered relatively creative if it can generate creations that are indistinguishable from those of a hypothetical human creator, as judged by an evaluator. This notion of creativity is subjective and depends on the individual being compared, allowing for an empirical investigation into whether an AI model can replicate the creative capacities of a predefined human benchmark. Section. Measuring statistical creativity of autoregressive model. In this section, we're going to discuss how we can apply the concept of statistical creativity to autoregressive models, which are a key component of large language models, LLMs. These models are known for their ability to generate creative content. We're particularly interested in how statistical creativity works in the context of predicting the next token in a sequence. Our main idea is simple. If an AI can generate sequences, like poems or stories, that are similar to the works of a group of human artists, then we can say that the AI is as creative as that group. To measure this, we introduce a metric, which we'll call 37. This metric estimates how similar the creative abilities of an autoregressive model are to those of human creators. It does this by measuring the likelihood of next token predictions across different pairs of creators and their creations. In this formula, the pairs are chosen randomly and uniformly. The term of interest is where we define the true, but unknown, distribution of creations for a particular creator. We also consider the entropy of this distribution. We set a positive constant as a threshold, which we'll discuss in more detail later. When we break it down, a creation consists of a certain number of tokens. We define a term and represent another term. The term is based on a context window size. For certain conditions, the expression simplifies. Similarly, for other conditions, the notation changes. In simple terms, an evaluator can't tell the difference between a synthetic AI creator and a real creator if the divergence between the two is minimal. We make the following assumption to make this concept clearer. Within this context, we define a threshold that fulfills the condition in our assumption. We also introduce the smallest positive real number that ensures a certain condition with near certainty. This assumption outlines the conditions under which an AI is considered statistically creative. With this condition, we present a theorem that measures statistical creativity in the next token prediction setup. Next, we discuss how to measure statistical creativity in large language models. Prompting is a powerful technique for unlocking the potential of foundation models, especially LLMs. In this setup, we denote a set that includes various contexts of creations. Each context within this set is represented by a term. We define a probability distribution over this set. We define another term, where a sequence of existing context prompts is assumed to be independently and identically distributed. We also define a term that corresponds to a possible new context prompt. To illustrate the difference between two variables, consider the example of GPT-4. Here, the creator's information, such as a biography, is represented by one variable and serves as the system prompt, while the other variable corresponds to the user's input prompt. To measure statistical creativity in advanced models, we modify our previously defined functions to include the user's input prompt. As a result, functions are updated. This change is consistently applied across related definitions. For example, a term is redefined, where a term represents the combined user and system prompts. Based on these changes, we redefine statistical creativity. This definition expands upon our previous definition by incorporating it into a prompting setup. We then present results that are similar to those discussed in the previous section. We introduce a metric, where a term is defined. We also define a term where a triple is defined with a term. We define another term. We let a positive real number be such that a condition is almost surely met over a set. Then, we present a corollary for prompt-contextualized autoregressive statistical creativity. The corollaries we've presented expand on our previous theorems, showing how our creativity framework can be extended and reimagined with the introduction of a prompting setup. This not only enhances our framework but also helps us better understand the behavior of large language models. Section Summary. In this section, the authors explore the concept of statistical creativity in the context of autoregressive models, which are essential for large language models. They propose a metric, 37, to measure the indistinguishability between the creative abilities of an autoregressive model and human creators by evaluating the log likelihood of next token predictions. They also introduce the notion of a prompting setup, where they expand their functions and definitions to incorporate user and system prompts, and present corollaries that extend their creativity framework in this setup. Section. Achieving statistical creativity through training. In the previous sections, we've been discussing how to set up a framework to determine if trained models show statistical creativity. Now, we're going to tackle a key question. How can we guide a model to achieve creativity? This section is dedicated to clarifying this approach. We'll revisit terms we've previously introduced related to statistical creativity, with a special focus on terms like 92 number 92 and 93 number 93. These terms can be derived, suggesting a way to define statistical creativity loss, an equation. This concept is the core of our approach, connecting the theory of statistical creativity with practical ways to assess and improve the creative abilities of AI models. We'll use the same notation as in section, where 79 number 79 represents the combined user and system prompts. We'll consider a learning algorithm 95 number 95 and denote its output as 96 number 96, given the sample set 97 number 97. This is done under the condition that 98 number 98 almost surely over 99 number 99, where 100 number 100. Also, for the following discussion, we define 101 number 101 where 102 number 102. A crucial part of our discussion revolves around the concept of generalization in deep learning. We introduce a placeholder notation 103 number 103 to represent potential overfitting of the model to its training dataset. We chose to use a placeholder because the exact metrics and quantifications of overfitting, captured by 103 number 103, are currently a hot topic in research on generalization bounds. This modular approach allows us to easily incorporate future advancements in the study of generalization into our framework, by simply updating the placeholder, 103 number 103. For clarity, we'll also present some potential manifestations of 103 number 103 based on the current understanding from the study of deep learning generalization. Specifically, for any 104 number 104, we define 103 number 103 such that with probability at least 105 number 105 over a draw of 100 number 100, the following inequality holds. Several foundational works have explored the complexity of deep neural networks. For example, with the Rademacher complexity bound, the size-independent sample complexity of neural networks provides 107 number 107 where 108 number 108 is the number of layers of the network. 109 number 109 is the upper bound on the Euclidean norm of the network, and 110 number 110 is the upper bound on the Frobenius norm of the weight matrix at the 111 number 111 th layer. In addition, with the recent result in information theory, we have 112 number 112 where 113 number 113 is the conditional mutual information between the network input 114 number 114 and the output 115 number 115 of the 111 number 111 th layer, conditioned on the target label 116 number 116. Here, 117 number 117 is the mutual information between 97 number 97 and the set of weight parameters from the first layer to the 111 number 111 th layer. Moreover, the sample complexity based on robustness indicates 118 number 118 where 119 number 119 designates a chosen compact space of 120 number 120 relative to metric 121-121. The constant 122 number 122 is Lipschitz and defined as 123 number 123 for any pair 124 number 124. Notably, 125 number 125 is the 126 number 126 covering number of 119 number 119. Furthermore, for any model configuration, if we chose 127 number 127 with 128 number 128, and use of concentration inequalities provides 129 number 129. Unlike traditional discussions on model generalization, which often focus on metrics like classification accuracy, corollary studies the creative performance of models trained using the statistical creativity loss equation. This shift in focus highlights our commitment to exploring and understanding the unique aspects of creativity in AI models. The proof for this is presented in the appendix. In this section, we'll give a brief overview of previous definitions of creativity and its applications in language and vision. Research into creativity has been ongoing for several decades, and it remains a key interest in psychology, cognitive science, and philosophy. Despite the wealth of research, there's no universally agreed upon definition. In fact, there are over 100 proposed definitions, highlighting the multifaceted nature of creativity. In the field of computational creativity, a commonly accepted framework for assessing creativity uses the 4 Ps: person, the creator of a work; press, the environmental context for a work; process, how a work is created; and product, the work itself. One study presents a triadic criterion for gauging machine creativity, emphasizing artifacts or ideas that are new, surprising, and valuable. Building on this, another study identifies three nuanced forms of creativity: combinatorial, exploratory, and transformational. This classification combines the process and product dimensions of the 4 Ps to focus on the production of surprising or novel outputs. Previous works consider absolute creativity at the level of each creation given each environment without mathematical concreteness. We depart from this approach. Instead of considering absolute creativity at the creation level, we consider the relative creativity at the meta-level of parallel universes consisting of humans and AI algorithms. This allows us to avoid the question of what is creative in an absolute sense, and thus enables us to rigorously define objectives and desired properties via concrete mathematical formula instead of English descriptions. Section Summary. In this section, the authors discuss how to steer a model towards achieving creativity by defining a concept called statistical creativity loss. They also introduce the concept of generalization in deep learning and present potential manifestations of overfitting. The authors emphasize the shift in focus from traditional metrics like classification accuracy to evaluating the creative performance of AI models. Additionally, they provide an overview of previous definitions of creativity and highlight the need for concrete mathematical formulations to define objectives and desired properties. Section: Applications in Vision and Language. The realm of image generation models that can create unique and innovative visuals has seen a significant surge in recent years. This has sparked curiosity about the potential of machines to generate artistic creations. Some researchers have explored this intersection of computer graphics and artistic creativity. They have introduced 3D modeling techniques that can create designs in line with user preferences while also ensuring diversity. Generative adversarial networks, GANs, a type of machine learning model, have been used to create unique artistic styles. They do this by maximizing the differences from known styles. Some researchers have taken this a step further by encouraging these models to create styles that are different from those in their training sets. The idea of creative generation as a process of composition is evident in some works. These works emphasize the importance of integrating detailed elements into the final creation. Some researchers have built on this idea by breaking down personalized concepts into visual elements. These elements can then be reassembled in innovative ways, enriching the creative output. In parallel with these advancements in visual models, there has been a similar evolution in language models. Researchers have been exploring ways to optimize the use of data to improve these models' adaptability across various domains, tasks, and languages. There is a growing trend to use language models to understand the subtleties in human communication. This understanding is then used to improve classification models. With the rising popularity of generative models, there has been an increased interest in controllable text generation. In this type of model, the output must meet certain constraints, such as politeness, sentiment, or other stylistic requirements. Text style transfer, TST, has also become a popular task. In TST, the goal is to change the style of a given text to match a target style. This style could refer to a variety of text and author-specific features, such as politeness, formality, simplicity, author gender, and more. While all these applications aim to incorporate elements of creativity in generative models, none of them directly define creativity or aim to optimize for it. Instead, they focus on improving the model's ability to perform predefined tasks, which are used as proxies for creativity. In contrast, our research focuses on establishing a theoretical foundation for creativity. This framework naturally includes previous insights on diversity and the quality of generation. We hope that our contributions will pave the way for future work, guiding the enhancement of model creativity.